Hello, this is a demonstration of power lines and transformers. So what I have here is my power station end of my power lines, and then you can perhaps just make out here a couple of very long and thin wires going all the way along to, here they are, the domestic end. This is where I want to light my light bulb up. That's my light bulb there in my house. Okay, so what I want to do is put 3 volts across that light bulb at the end there to light it up. And you can see I've got multimeters connected, one at the power station end, and there's another at the end where I'm trying to light my light bulb up. So we can see the potential difference across here and across there. Okay, so what I'm going to do first is I'll be getting my power from the mains here. That's coming out about 240 volts. I'm going to need to step that down actually, so this transformer is just to step it down to the 3 volts that I require. So we're dealing with a 3 volt supply. I've got a test light bulb here as well at the power station end, just so you can see that we are doing something in the circuit in the first instance. Let's turn this on and see what happens. So we're putting 3 volts into our power lines. There we go, our light bulb at the power station end. That's the light. And you can see we're getting 3.2 volts there. So the PD here is 3.2 volts. Let's see how we're doing down at the domestic end where we actually want the light bulb light. So here we go along the power lines. We're back over here. Problem. My light bulb is not alight. Okay, so what can I do about that? Well, let's have a look here. We've got 0.04 volts across this light bulb. What has happened? Well, as you all know, wires are not perfect. They do have resistance, and we have some very long wires here, long and thin wires, so the resistance is very substantial. What has happened is the 3.2 volts that we're putting across here, most of the PD is across the resistance in the wires. So most of the power that we're putting in at this end is being dissipated as heat in the resistance wires. So we're only left with 0.04 at this end, which is not enough to light our light bulb. So what can we do to rectify the problem? Well, as you all know, the answer is transformers. So what we're going to do is, instead of putting this 3 volts directly across the power lines, we are first going to step up the PD. We're going to take our 3 volt input here, and we're going to step it up by ratio to give us about 24 volts PD. I'm going to put that into the power lines. You have to be careful here. This bulb will not tolerate 24 volts across it, so we'll need to take that one out at the power station end. But we still have our multimeter here, so we can see what the PD is. Okay, why would I want to step this up to 24 volts? So when I step this up to 24 volts PD, the current will be proportionately reduced in the power lines. That's important because the power losses due to the resistance in those wires is equal to P equals I squared R. So if I reduce the current, then that power loss reduces dramatically by a squared factor. So that's really good. I can reduce my power losses now. So now I can get a much more efficient power transmission over to the domestic end. Okay, do I need to do anything else? Can I just put my 24 volts across there? If we go over to the domestic end now, in order for this to work safely and correctly, I am going to need to do something to the supply at this end, because although there will still be some potential difference from the power station going across these lines, the PD won't actually be reduced to the point that I can safely light the light bulb up. It will still be too large. So in order to correct that, I'm going to use a step down transformer at this end. So I'm stepping up from 3 volts to about 24 at the power station end. I need to step it down from 24 to 3 volts at this end. So this is my step down transformer. This is where I'm going to put my inputs from the power lines, like that. And then the output, 3 volts, will go across the light bulb. Okay, so we've got a few more wires to handle here. I'll move the camera position over to here. So now you can see our light bulb again, and you can see the multimeter with our step-down transformer in the background. Okay, so now let's turn on the power and see what happens this time. There we go, we can light up our light bulb, and we're getting 3.2 volts at this end. So go over here, and there we go, we've got 27.5 volts going in at the power station end, and our 3.2 at the domestic end. And this is really the reason why we use AC in national grid systems. It enables us to use transformers. Transformers only work with alternating current. So by using alternating current, we have the ability to step up our supply so that we can get more efficient power transmission across very long, thin power lines, and we can then step it back down for use wherever it needs to be. It may not be a house, it may be a factory or some other energy user, but ultimately, whatever use it's going into, it would require stepping down that potential difference to something that we can use for whatever context it is.